This is a very brief review on two topics in one in electromagnetism and one in quantum mechanics that we shall need for the topic on Meissner's effect of superconductors. And the first topic in electromagnetism is about vector potential. I shall briefly review what this is about. The definition of a of the vector potential is usually given as the curl of A equals to B, where A is the vector potential and B is the magnetic field. Now that is usually all there is if you look at textbooks. Alright, in simple language, we can even just say that the vector potential A is defined as the thing whose curl is the magnetic field. So physically, it doesn't mean very much. But in this review, I'm going to briefly explain what it means physically and also briefly look at how we could understand the shape of this field for the simple case that we shall need for Meissner's effect. So I shall first look at the corresponding, the related Maxwell's equations that we shall need. And since we will be switching between the differential and the integral forms of Maxwell's equation, it would be good to remind ourselves of the Stokes Theorem. So the Stokes Theorem is the result from vector calculus, which says that if I have a loop, say in three-dimensional space. Now let me call this loop L. Okay, and suppose that this loop is in a certain vector field. In general, the vector field can be the magnetic field, electric field, or in this case the vector potential. So I just let this field be A, and it's a vector field in the sense that it's a function of position in space, so function of x, y, z. Okay, so Stokes' theorem says that if you think about a short section of this loop as a vector dl, and if I take the dot product of A and L and integrate it around the loop, okay, then the result is equal to, if I take the curl of A and take the dot product of the curl with now we're going to think of a surface, just any surface that is enclosed by this loop, that has this loop as the boundary. And we are going to imagine a small area called ds. And we are going to think of a vector that is perpendicular or normal to this area with the same magnitude as the area element ds. And we are going to think of ds as a vector. So dotted with this ds, vector normal to the area, little area, and integrated over S. So that's the statement of Stokes Theorem that is needed for Maxwell's equation. Okay, so we would be using it for the vector potential as well, since it involves a curl. So let's start with the Maxwell equations that we need. Now, the first thing that I'm going to look at is to see how we can visualize A in the same way as we would visualize a magnetic field. So let's start with Ampere's law. So this is one of the 4 Maxwell's equations. In Ampere's law, a simple example involves a straight conductor, just a piece of wire, with a certain current density. I shall call that J, vector J. Okay. Now, when I have such a current, we know that there would be a magnetic field around it whose direction is given by the right-hand thumb rule. So a magnetic field goes around the loop like this. So lots and lots of concentric circles around the wire. And Ampere's law tells us that if we integrate the magnetic field dotted with a short section of this loop, okay, this loop L, and if we integrate this dot product around the loop, then this answer would be related to the current density in this way. Now imagine a surface with this loop as the boundary. So any surface, I'll call it S. And again, imagine a little area here, ds, with a direction normal to that area. Now, so if I let me just correct that. The field should be in that direction. That's the right-hand thumb rule, isn't it? Okay. If I take the curl, no, not the curl yet. Let's see. The current density and dot it with the area element. This gives me the current going through that area and integrate it over the whole surface. So this is basically the total current that goes through the loop, and multiplied by mu naught, the magnetic permeability in free space, then the answer should be equal to this integral on the left. That's the statement of Ampere's law. Now, using Stokes theorem, this is also written. By the way, there's supposed to be a displacement current term involving a changing electric field. Alright, and with some other symbols around it. But I'm going to assume that in this example, there is only a straight conductor with no capacitor in between. So therefore, that's just 0 in this case. Alright, and in the differential form, which we can obtain using Stokes theorem, in this case, we could do it by replacing by using this formula, right? But we have A dot dl there and we have B dot dl there. So just substitute the B into the A here. In this case, think of the A as an example of a vector field, not necessarily the vector potential yet. So just substitute B into there, and then we can have it in terms of the curl. Okay. So that becomes the curl of B dotted with the area element integrated over the surface. And we have this equation. And then the argument is that since the left side and the right side are always equal, regardless of the surface or the loop that we actually choose, meaning that we can choose the surface to be, or the loop to be big or small or anywhere in space, right? You can include the wire, or it does not even have to include the wire. So since this is true for any surface or loop, the integrand, that means the thing inside the integral, on the two sides have to be equal. Otherwise, if there are positions in space where these are not equal, then I can always choose the surface to be in those positions, and then the left side would not be equal to the right side anymore. Okay, so we have this result here, that the curl of B is related to the current going through it. Now let's look back at our definition for the vector potential, that the curl of A is equal to B, and compare it with what we have now with this differential form of the Maxwell's equation. So what we have here is the vector potential, curl of A equals to B. And you can see by comparing the two that they are very similar. Now this similarity gives us a way to visualize the vector potential for a simple example. Now to see how we can make use of this, look at this example. Alright, this is just one example of this equation. Alright, in the sense that in this example, for a given current density going this way along the wire, along a straight wire, that would be a circular field around the wire. And this equation basically implies this connection between the two. Alright, we know that this is true from experiments, from observations, but the idea of Maxwell's equation is that if we start from this equation, and if we are given say a current density, a uniform current along a straight wire down here, we can actually solve this equation for B, and that would give us a solution, and we would find that that solution is actually a field with these concentric circles around the wire. So in this sense, this equation governs the relation between the two, between this term here and this term here. And in this example, we know that if that term there is a uniform field, okay, we can also think of this current density as a field since it has magnitude and direction, and it could change at different positions. So if you have this field, which is this uniform parallel thing, okay, then and if it's related to that field B by this curl, then that field B must go around in circles. Now with this understanding, let's now think about applying this result to the vector potential. So from what I've said, if that field, that magnetic field is a parallel and uniform field like the current there, then the magnetic potential must be a circular field. So let me sketch this out. So suppose I have a magnetic field that goes this way, just like that current density up there. Then the corresponding vector potential must look like this. So we have just visualized A for a simple example. And once we have this picture, the vector potential would no longer be just something abstract, something whose curl is B. Alright, we can actually draw a picture and show that, right, this is what A looks like if I have a B there. Now just to make it more realistic, we might want to think of how we could actually create a magnetic field that looks like that. After all, it is no good if it's completely imagined. So, and indeed we can make such a field using a solenoid. So imagine if I have a wire that goes round and round, this bundle of arrows, then and I send a current around it that way, the right hand thumb rule again, that would produce a magnetic field going that way. So a wire that goes around this way. So this time this is a wire that's not part of the field. And I send a current through it. So the current goes through this solenoid, okay, and this would produce a magnetic field. And And the magnetic field, as we have seen, would in turn produce this vector potential field. So now we even know how to produce a circular vector potential field. So we have just visualized the vector potential for a specific example. So in the next part, I'm going to show that the vector potential can actually be understood as a momentum of the electromagnetic field. A momentum, well, in the same way that we know that the electric potential is related to work done when you move a charged particle through an electric field. So let's look at the how this is the case. Now to do this, we need the Faraday's law. I shall write down these statements of the Faraday's law. Right, again, it is easier if we have something to visualize. Now, Faraday's law, when we learn Faraday's law, we usually learn this example of a coil of wire and when we have let's say when we bring a magnet towards this coil of wire, that would induce a current. Okay, so that's Faraday's law. So as you move this magnet towards it, the magnetic field through the solenoid changes, and this change in the magnetic flux would induce a voltage around the loop. Now, in fact, the voltage is induced. Okay, we can think of the reason why the voltage is induced as a result of a circular electric field being created around the changing flux. So that circular field would not just be limited to inside the coil of wire. It is in fact spread all over the surrounding space. Okay, so you have this electric field that goes around. So that's an extension of what we would learn as an example of a setup for Faraday's law. Okay, and this extension of the idea of just having induced voltage within the coil is basically what the Maxwell's equation tells us, or is basically what leads to the Maxwell's equation, which is given by the integral of E dot dl, where we think of a loop L, let's say maybe that loop. Okay, and dl as a short section on the loop. So when we think of this loop, this is the electric field, which is actually the force per unit charge, dotted with dl, which is a short distance. So if you think of force times distance, that's basically the work done, and this is actually the voltage, okay, which is the work done per unit charge. Alright, and Faraday's law says that this induced voltage is equal to the rate of change of the magnetic flux. Now the magnetic flux going through this loop is given by the magnetic field times the area, so it can change at different positions. So let me just imagine a little square here that could be an area element ds. So it has to be integrated over the whole surface that is enclosed by this loop to get the total flux. So that's a statement of Faraday's law. Okay. Now, let's look at these two pictures together. I have a flux here, changing flux, that induces a circular electric field. I have a magnetic field there that produces a circular vector potential field. The similarity is obvious. A corresponds to E, and this similarity means that we can try and look for a connection between the vector potential and the electric field. And we can find this connection by looking at making use of these two equations, this one and let's see. We don't have a corresponding one for A. So we need a corresponding one equation for A, meaning we need an integral form of this equation. Now to make the integral form, let's make use of the Stokes Theorem. Okay, so if I have a curl, the integral form would be just this. Alright, I would just integrate this and get the integral form. And since I even have this formula using the symbol A, which is the same symbol I'm using for the vector potential, I can simply take over this formula and copy it down here. Now first I would take this and I would integrate the two. Okay, I would integrate it with respect to ds. So dot ds here and dot ds there. And the curl of A dot ds is just equal to, is the same as that, which is equal to A dot dl. So I would now write this in place of this and say that that's equal to the B. So let's write this down here. Using Stokes Theorem on that, I get the integral of A dot dl over the loop L, and on the right side it would be B dot ds. Over the surface. Okay. Now let's compare this with this. You see the B dot ds there and the B dot ds there. So these are both magnetic flux. Okay, then clearly on the right side, you see a clear correspondence between E and A. Right, the additional thing that we have there, oh, I forgot the minus sign in Faraday's law. So the additional thing that we have here is the d over dt, the time rate of change of this. But we can already see a direct connection between the E and the A in this equation, both in the equations and in the picture. So let's find this connection. Now, think about the change in the magnetic field in a short time, delta t. And think about the effect this would have on, let's say, a charged particle here with a charge q and a mass m. Okay, that's what we're going to do. So, but first, let's extract the connection between the two from the equations. Now, in the first step, move the dt there over here to the left. When we do that, I move the sign over there as well. Okay, when we do that, we will get an expression that looks like this. Minus dt times E dot dl is equal to minus is equal to the d there would refer to a change in the b, so I put it next to the b dot ds. We'll get an equation like this. Okay, when I bring minus dt over to the left. Now it looks very odd to have a dB dot ds down here, so I shall think about this as a small change, just a delta t and a delta b. Okay, so this is you can think of this as the effect of a small change in the magnetic field over a short time delta t. It produces an electric field for a short time, and they're related by this equation. Now let's look at the corresponding effects on the vector potential. Now that's easier to write down. If there is a small change in the B, that would lead to a small change in A. If we now compare these two, you see that this is exactly equal to this. Therefore, we can simply say that delta A must be equal to that. So let me write that down. Delta A is equal to minus of E times delta T. So that comes from here. Okay, we're nearly done. And from here, we can derive the connection between A and the momentum. Now to derive this connection, recall that the electric field is connected to force in this way. If I multiply both sides of this by the charge, then charge times electric field is the force, and we also know the meaning of force times time. Force times time is the impulse, and according to Newton's second law, impulse of the impulse on a particle is equal to the change in momentum of the particle. Okay, that's a change in the momentum. So now we have our interpretation. The vector potential A is a momentum. Now to clarify this a little bit, let's recall what we know about the electric potential. Remember, the gradient of the electric potential, and with a minus sign, is equal to the electric field. Okay, and if you remember how we use electric potential, we think of it as work done on a charge. Work done per unit charge, in fact. So that if I have a change, so that if I move a charge from one point to another, I would have a change in potential. Okay, and if I multiply the change in potential by the charge, I would get the work done on the charge by the electric field. So in the same way, therefore, we can think of the change in vector potential as the momentum given to the particle. Alright, now there is the sign there, so let's put the sign in. Let's just make this connection more obvious by doing this sign properly. Now see if let's see when work is done. Now work is done when there is a fall in the potential, like when you drop a stone. So when you drop a stone, then the gravitational potential falls. So likewise, when a particle is attracted by a field and moves it as a result, the electric potential at the particle falls, and in that way work is done on the particle. So as the particle gains in work done, alright, the potential that at its position falls. So therefore we need a decrease in that, which is a negative change, to give an increase in the work done on the particle. So therefore in this relation we need a minus sign there, alright, to cancel away this minus sign from the decrease in potential, to give a positive answer for the increase in work on the particle. So we have a minus sign there. Okay? So now the connection is clear. A decrease in potential at the particle leads to an increase in work done on it. So therefore, a decrease in vector potential at the particle leads to an increase in momentum of the particle. So in this way, we have our physical interpretation, and the vector potential A can be described as a field momentum. Now we are now ready to take this idea and use it on quantum mechanics of a particle in a field. Now let's start with the very simple example in quantum mechanics where we have just a particle of mass m, let's say moving with a speed v along, say, the x direction. The Schrodinger's equation for this system, just a particle in free space, no potential. Schrodinger's equation is given by minus of I h bar d of the wave function by dx is equal to the momentum times the wave function. Okay, and in this case we would think of the momentum as just mass times velocity. And we know how to solve this equation. The solution is psi equals to e to the power of let's see, I the best form to do this, I'll write it as ikx times some constant. Okay, a is not a good letter to use for constant. You're going to confuse it with vector potential. I'll just call it b times some constant. Now for our purpose, it's just a constant factor, so I'm going to drop it for now. Just look at the physical meaning of this exponential. Okay, it's going to have this form where k right, okay. To see what k is, we can simply substitute this into there. And if we do that, we substitute this into there and there, gives us minus IH bar. When we differentiate this, we would get IK E IKX is equal to, okay, P, that's P, and that's just this. Right, if we then make some rearrangement, can cancel that. Minus I times I is 1, so we can cancel those. Okay. And then we can find K. That's just P over H bar. Alright, that's also how we would get the relation that momentum is equal to H bar K. Or rather, we can think that this relation leads on to that, because that came from the Broglie's relation, that P is equal to H over lambda. Alright, so we have our solution for the wave function. Now, in the next step, let's think about what happens if this particle of mass m also has a charge q, and it moves in an electromagnetic field. If that's the case, then this equation there, this Schrödinger's equation for the particle, it has to be changed. Now, I should just mention here that this equation is a postulate in quantum mechanics. In other words, it's an assumption. It's not derived from anything, although it is often thought to be closely connected to some theories in classical mechanics called the Hamiltonian, and it has been shown, a set of rules has been developed to relate this to the Hamiltonian method. But for our purpose, let's just think about this as a postulate, as an assumption that works, okay, in which the d by dx is related to momentum. So in the case where the particle has a charge and this is in an electromagnetic field with vector potential A and an electric potential V, let's look at how this postulate, how this equation would change. Now, the more familiar change is when we have the Schrödinger's equation. We would simply add on the potential to the equation. Okay, the electric potential V. Now, what is more subtle in this case is what happens if we have also a vector potential. Now, this part is easy because the V refers to energy, and we simply add it to the kinetic energy term in Schrödinger's equation. But in this case, because A is in fact the field momentum, we need to add it here to the P. So if I write down the postulate now, okay, it would be the same, same as that, except that this time this time P is not just mv. P must be mv plus the field momentum qa. Alright, if you remember, that's what I obtained just now. Yeah. See. There. So that's the part where I showed that Q times the change in A gives a corresponding change in momentum of the particle. So because of this connection, we need to add the field momentum to the particle's momentum in the same way as we would add the electric potential energy to the kinetic energy term in the Schrodinger's equation. So that, in effect, is how the Schrodinger's equation for the momentum wave function for the momentum needs to be modified by adding that term. Now this change in itself is also not derived from anything. Alright, the need to add this. It just seems to be a logical thing to do, and this in itself is in fact another postulate in quantum mechanics. Another postulate that works. So we are going to see how to apply this postulate to Meissner's effect in the next video.